All right, so this chapter, force. There is, in the previous years, in ninth and all, you learn about force formula, which is force is equal to mass into acceleration. You're familiar with this formula, right? So what is this what does this explain about force is that for a force to be produced, there has to be two things, two quantities. There has to be mass and there has to be an acceleration. Mass means every object has mass. There's nothing that doesn't have mass, right? So anything you move has mass. What is the meaning of acceleration is an increase in speed. Okay, so there has to be an increase in speed. Increase in speed means either from zero to something, or if it's already moving, then speed has to increase, right? For example, if I push a box, am I applying a force? Yes, if the box moves, because it's moving from zero speed to a certain speed, right? So there is an acceleration, increase in speed. But suppose I'm pushing a wall, I'm not applying any force because there is no acceleration. There is no increase in speed. The speed is zero only. It's not changing, right? Yeah, but in this chapter, you're not learning about this formula for force. You're learning about another formula for force. You're learning about something called turning force. This force is when the force is in a straight line and the object is moving in a straight line. Okay. So here in this chapter, we're learning about something called moment of force. Moment of force is a turning force. So when you apply moment of force, it causes an object to rotate around an axis. Okay. So that's why we have two types of forces here, translational and rotational. Translational is also called linear, which is in a straight line. That's when we use this formula F is equal to m into a. But we are learning about rotational motion. That is when an object is, when a force is applied and it causes the object to go in a circular direction. Now, can you give me some examples of rotational motion? Okay, fidget spinner, but you have to turn it. Okay, fan, yes, it's turning. Anything else? Wheels of the car, steering wheel of the car. A door, when you open and close the door is going around an axis, right? Yes. So these are all examples where moment of force is felt. Okay. Now, moment of force is also called as just moment. You can just use the word moment, or you can use the word torque. Now, torque is a very familiar word when we speak about vehicles. If you're buying a vehicle, oh, what's the torque on this vehicle? Right, you've heard that. They talk about horsepower and torque. Right. So what that torque means is how much turning force that engine has or the motor has that's making that car to turn. Like how much, it's not how fast it can go, but it's how much force it can uh, pull. Like for example, it's like a pickup truck has a lot of torque because it can pull something heavy, carry a lot of weight, okay, carry a lot of load. So that is torque. Now torque depends on two things. So for that we have to look at the formula for torque. The formula for torque is magnitude of force, how much force is applied, multiplied by the perpendicular distance from the pivot. Okay, now I'll give you an example of a door. Okay, say this is the door, this is the pivot of the door, this is the door. Okay, here the handle is. Okay, now when you open and close the door, it turns around the pivot. This is the pivot or the hinge. It's attached on the hinge. Okay, now a more moment of force. Okay, someone's coming. Just a minute. Come, Ryan. Come sit. I thought you were joining online. I'm also joining online. Sit. Okay, we just started the first chapter in physics. Okay, so we're talking about, just repeat that. Okay, moment of force, not force. Force is a straight line force. We're not talking about straight line force. We're talking about moment of force which causes an object to rotate around an axis, like opening a door or turning a tap. You know, when you close the tap, it's turning around the axis. Okay, so this moment of force depends on two factors. It depends on the force applied. See, when you open the door, you're applying force at which part of the door? On the handle, right? They're applying force. So that force is one factor. Second factor is the distance from the hinge, perpendicular distance from the hinge. Now, this is the hinge. From the hinge till that knob, the door knob or the door handle, that distance. Okay, so moment of force depends on these two factors. Okay. Now, let's understand how it depends on both these things. For example, there's a door, a very heavy, big door, like a door of a castle. You know, Stiaga doors, how it is, very big. Okay. Now, say we go to the door and now we have to open the door. It's a very heavy door, so you need a lot of force to push. Okay, now if I and my daughter go, Noe, and we both are pushing, who has more force? Who has more strength? I'll have more strength, and she will not have less. She won't have so much strength because she's small. So the amount of force she's able to apply is less. Okay. So what this formula says is the more force you apply, the more turning force is felt. Means you can turn that door. That's the first factor. The second factor is the perpendicular distance. Means how far the hinge is, how far the handle is from the hinge. If you're trying to open, like okay, say this laptop. See, this is also turning force. Okay. Now if I try to close this laptop from here, it's very hard to turn it. Why? Because the distance I'm trying to, what if those are online can't see, but what I'm doing is I'm trying to, okay, let me give another example. Okay, here, this is also turning force. Okay, see now if I try to turn it from here, it's very hard. Okay, but if I turn it from here, very easy. I can use my tiny finger also and turn. So what happens is the farther the distance is from the hinge, the more moment of force is felt. You understand? The farther, that's the distance. If the perpendicular distance is more moment of force is felt. You can turn this easily. See, if I try to push from here, it's really hard. But from here, it's very easy. Do you understand? Have you tried this? Have you ever felt this force? Like the farther you go away from the hinge, the easier it is to turn something. No? Okay. So I don't know if I've given you this example, but night channel I told about when I was opening a nut in my car. No? Okay. So few years ago, I went under the car and there's a nut that I have to open to drain the oil from the car. Okay. It's very tight. That nut was very tight. And I had a very small spanner around this long. This long spanner I had. No, it's a spanner, no? So I put the spanner on that nut and I'm trying to turn the nut. Yeah, I'm under the car. So I'm like putting it there and I'm actually literally hanging on that spanner, but the nut is not opening. So what I'm doing, I'm applying my maximum force. I have a certain amount of force, my weight, my whole weight I'm applying, but that force is not enough to open that nut. The second thing, what I could have done is, I could have increased the distance. How do I increase the distance? My spanner is so small, huh? I'm already holding at the end and it's not opening. Can I increase the distance now? What do I do to increase the distance? Yes, I need a longer spanner. That's all. So I went to my friend, Rajiv Dada, and I told him, do you have a longer spanner? So he gave me a spanner so long. With that spanner, I just put with one hand only I was able to open it so easily. Okay. So when I increase the distance, what happened to the total moment of force? It increased. Okay. So that is how we can increase moment of force. We have two ways. Either increase the force. I cannot increase the force anymore because I used my maximum force. If I have to increase force, I need to call someone. Maybe I call Ryan. Maybe he has more force, right? So that's the way I can increase force. Or the second way is I can increase the distance. That's what I did. I increased the distance so that I could turn it. Is this clear about moment of force? It's like opening the door or opening anything. It's easier to open it from away from the hinge. That's why they place the handle away from the hinge. They don't place the handle right next to the hinge. Clear, everyone? Okay, so this is the formula, force into perpendicular distance. Now let's talk about the units. What is the unit for force? Unit of force? Newton. N, right? And the unit of distance? Meter. So the unit for moment of force will be Newton meter. Clear? All right. Okay, just write down the formula for moment of force and the units. Before you write that, let's read the definition for moment of force. The definition is very easy. It is just the formula itself. See, the moment of force or torque is equal to what? The product of magnitude of force, that is F, and the perpendicular distance of the line of action of the force from the axis of rotation. The perpendicular distance, okay, if this is a door, the distance of the hinge should be perpendicular from the hinge. It should not be like cross distance. It has to be perpendicular. Clear? Okay, so that's the definition. Can you try to say the definition? What is moment of force? It is the product of two things. What all? magnitude of force and perpendicular distance. Distance from where? Distance of the line of action means where you're applying the force. From where? From the axis of rotation. That means the hinge. Okay, write down the formula.
No, whatever small vehicle you have will same torque as what
Then it will just slip. The wheel will spin because it's not heavy enough to be able to pull that load. Like it will try to go forward, but it's not heavy, so wheel will spin.
and should because
It has to be heavy also. That is one factor. It has to be heavy and have a high torque. Then it can pull. Okay, turn writing now. So this unit that we have written is the SI unit. Newton and meter are the SI units, right? What is the smaller unit called? SI and CGS, right? So let's write on the CGS unit. SI unit is, let me make a table. Moment of force is represented using which alphabet? Which is writing moment. Okay, so moment is equal to force into perpendicular distance. The SI unit okay. Now let's derive the CGS unit. Okay, the CGS unit. What is the CGS unit for force? Dyne. And the CGS unit for meter is centimeter. Okay. So obviously the CGS unit would be what? Dyne centimeter. Okay. Now let's see the relationship between Newton meter and Dyne centimeter. Okay, so 1 Newton meter means 1 Newton into 1 meter. Okay, here we're writing the relationship of SI and CGS unit. So 1 Newton is how many dyne? 1 Newton is how many dyne? 10 raised to 5. And 1 meter is how many centimeters? 100 centimeters, which can also be written as 10 raised to 2. So if we multiply these two, we're getting how much? 10 raised to 7 dyne centimeter. So that is the conversion. 1 Newton meter is equal to 10 raised to 7 dyne centimeter. Okay, done writing this? Now, Newton is a unit for what?
Force.
Force. There's another unit for force, not the CGS unit, but another unit that we use more often, kgf. Okay, now when we measure our force, our weight is our force that we're applying on the earth. We measure our weight in kgf actually, but we say kg. Okay, we're supposed to say kgf. So what is the relationship between Newton and kgf? 1 Newton is how many kgf? It's the other way. 1 kgf is 9.8 Newton. Have we seen this conversion? When do we see this 9.8? Acceleration due to gravity, 9.8 meter per second square. You remember that number? Okay. Anyway, remember this number. 1 kgf is 9.8 Newton. Approximately, we take it as 10 Newton. Okay, so 1 kgf is 10 Newton. Means if your weight is how much? What's your weight, Aman? 55 kgf. So in Newton, how much it will be? 55 kgf. 1 kgf is 10 Newton. So to convert kgf into Newton, we are doing into 10. So 550 Newton will be your force or your weight. You understand?
Yes.
So for finding your weight, you can either say in kgf or you can say Newton. We generally say in kgf, but we don't use it. We don't even use f. That is wrong actually, because if you remove the f, then kg is the unit of what? Kg is not the unit for weight. For weight, it is kgf or Newton. Yeah, kg is the unit of mass. Okay. Fortunately, on Earth, mass. I mean, so it's like this. Okay. I'll just write the units over here: mass and weight. So for mass, the unit is kg, and for weight, it is either kgf or Newton. 2 units for weight. Now, if your mass is 55 kg, in kgf also it is same 55. So number is same, just we have to use the unit kgf if we are saying weight. For Newton, you have to multiply with 10. So that would be 550 Newton. Okay. I'm putting a bracket here. Weight is also force. What's the difference between force and weight? Force can be in any direction. Weight is the force exerted by us on the earth towards the gravity. Okay, just write this much. This 1 kgf is equal to 9.8. We'll write that afterwards. After this. Now you write this mass and weight thing. Now we are talking about Newton meter as the unit of torque, right? So here I should use it. The unit will be kgf meter, correct? You're multiplying with meter, no? So Newton will be written as Newton meter for torque, and kgf will be written as kgf meter. So the conversion is same like this. 1 kgf meter would be 9.8 Newton meter. Now there's a smaller unit than kgf. What is the smaller unit? GF, gram force. This is kilogram force and this is gram force. And meter, small unit of meter would be what? GFCM. Okay. So how do we convert now? kgf meter into GF centimeter. 1 GF centimeter is 989 centimeter. Okay. Now, moment of force could either be clockwise or it could be anti-clockwise. Okay. If moment of force is clockwise, like if you're looking on the top view and if it's moving clockwise, we generally take clockwise moment of force as negative, and anti-clockwise moment of force, we take it as positive. So normally this direction, this is clockwise, is how you close a tap. When you close the tap, you turn it clockwise. When you open a tap, you open anti-clockwise. Okay. Anyway, you don't have to worry about tap over here because they won't ask about tap, but they'll talk about direction. So just remember, if it is clockwise, it is negative, and if it is anti-clockwise, that's positive. Okay. Now let us see some examples of applying moment of force. The first example was opening and shutting the door. We already spoke about that, right? When you open and close the door, how can you increase the moment of force? Either increasing the force that you're applying or increasing that distance. Then, okay, this is something that people used to use a long time ago. If they are grinding grinding flour, that grinding mill is there, no? Now it's all motorized, but before people had a handle and they had to turn that stone round and round, and that's how they used to powder rice or wheat. Okay, so that mill, no, the handle was far away from the center, so that you have a bigger circle to turn. Okay, if it is very close, no, then you need to apply a lot of force to make it turn. So the bigger the farther the, like there's the rim. Okay, if the handle is near the rim, then you have more moment of force to turn that. Okay, better example is the steering wheel. Okay, if the steering wheel is small for a car, then you have to apply a lot of force to turn it. But if the steering wheel is big, less force is enough to turn it. Okay, that's why if you see trucks and buses, they have very big steering wheels because the vehicle is heavy and you need a lot of moment of force to turn that. So to reduce the force applied by the person, they increase that distance. You can apply less force and you can turn it easily. Right? It's like the example of me opening that nut. When I increase the moment, when I increase the distance, I had to apply less force. I didn't have to apply so much force, right? So same way here, increasing the size of the steering wheel can reduce the force applied. See the formula? Moment is equal to force into distance. By increasing the distance, you can apply less force to turn. Okay. Then bicycle also. We have different gears. Okay. What is the purpose of the different gears? Okay. Now, first gear, uh, you look at the back gear, not the front gear. Okay. The back gear which you have on the cycle. When is it easier to climb a slope? On the first gear or last gear? First gear. On the first gear, how is the size of the gear? Big or small? Big. Okay, so when it is big, you are increasing the distance, right? So there's more moment of force felt, and you're able to turn. And on the last gear, how is the size of the gear? Small. When you put on that, do you have force? Can you climb a mountain using that? No. Okay, but that helps you to go faster. You get speed. So same effect on the uh, gears of a bicycle. Spanner. This is the example I gave you. Right. The longer the handle of the spanner, like you get more moment of force to turn that nut.
Is that gear system same for bike?
Yeah. But on the bike, the gear is not on the wheel; it is inside the engine. There they have the gears. And when it is over there, it's the opposite. The smaller the gear, the more easier you can climb the mountain. The bigger the gear, if you see your cycle, you can understand that. Right? To climb a mountain, it is easier to put on the first gear on the back. On the back, how is the first gear? Big. In the front, which gear you should put to climb the mountain? The big one or the small one? Small one. Okay, so that's how they work. On the back, you have to put in the biggest gear. On the front, you have to put in the smallest gear. Okay. Yeah, so for a bike, they have all the gears in that front part where the engine is. Okay, spanner is done. Next, a jack screw. Okay, if you're lifting a car, there is this jack. And we don't use that. We use a thing that goes round and round. But if you go to a shop where they change tires and all that, they have one long thing, one long handle. They'll put that section, that part under the car, and they'll just move the handle down, and the car goes up. Okay. So why do they give such a long handle? Yeah, to increase the distance. When you increase the distance, you just have to apply less force to cause that turning effect. Yeah, I'll just re-explain that couple I forgot to record. So moment of force is generally from one side of the pivot. So in this example, if you have a force of 5 Newton at a distance of 10 meter from the pivot, so the total moment of force would be force into that distance, which is 5 into 10, 50 Newton meter. Okay. Now we have something called a couple. Couple is when you have two, when you're applying force on both sides of the pivot. Okay, like say opening a tap, opening a bottle. These examples, you're applying force on both ends of the pivot. So there are two forces acting in opposite directions. So say A is one end and B is the other end, and the center pivot is O. So at the point A, you have a force acting upwards, and at B, you have a force acting downwards. And the forces will always be equal. So say 5 Newton force on the right side and 5 Newton force on the left side. And the from the pivot, the distance to A is 10 meter, and the distance to B is also 10 meter. So the total couple would be moment of force on the right side plus the moment of force on the left side. That is 5 into 10 for the right side and 5 into 10 for the left side. So that's 50 plus 50, which would be 100 Newton meter. Okay. So you can see over here that the moment of force is doubling for a couple. If it's only from one side, it's 50 Newton meter. But when you have a couple, the moment of force is 100 Newton meter. And here we have derived the formula for a couple, which is F into the total distance between A and B. F is 5 Newton. Don't add 5 plus 5 Newton. Just take one of the forces as 5 Newton, multiply that with the total distance between A and B. In this case, F is 5 and D is 10 plus 10, that's 20. So 5 into 20, which is 100 Newton meter. Okay, everyone clear about this? Okay, the next topic is equilibrium of bodies. Oh yeah, equilibrium of bodies. What's the meaning of this word equilibrium? Equilibrium just means a body at rest. That's at equilibrium. Suppose you're sitting without moving like this, then I can say that you are at equilibrium. Okay. But now in equilibrium also you have two types of equilibrium, static equilibrium and dynamic equilibrium. Now static means not moving and dynamic means moving. So static equilibrium means an object which is at rest. It's not moving at all. Okay. And dynamic equilibrium means what? Moving that is not moving. How does that make sense? First, what I said equilibrium is a body at rest, not moving. So what does it mean by dynamic equilibrium? So equilibrium doesn't mean that it is completely at rest. It just means that it is moving at a constant speed. See, like even if you're sitting at rest, you're actually moving because the earth is moving, right? So rest also is something that is relational. You have to see in relation to what. Okay. Anyway, here dynamic equilibrium means something that is moving at a constant speed. That is dynamic equilibrium. For example, a raindrop that's falling from the sky. The raindrop is moving at a constant speed. It might also be rotating, but again, it is rotating at a constant speed. So, such objects which are moving at a constant speed without increasing or decreasing their speed is called, that body is at dynamic equilibrium. Okay. So, static equilibrium is what? At rest, complete rest. It is just staying in one position, like this tissue paper box over here. It is not moving. So, that is at static equilibrium. And dynamic equilibrium means a body is moving, but it is moving at a constant speed.
And this time really good.
Yes, the span is moving at dynamic equilibrium because it's rotating at a constant speed.
The second line of clock.
Yeah, yeah, but that's stopping moving, right? It has to move continuously. Yeah, some clocks they keep moving without stopping. So that clock could be at dynamic equilibrium. And let's read the definition. Static equilibrium is when a body remains in a state of rest under the influence of several forces. The body is at static equilibrium. Okay, so there are forces acting on the body. For example, uh, this object in my hand over here, or think of a seesaw, and there are two people sitting on both the sides, and the forces that both of them are applying is equal, and so the seesaw doesn't move. So that time we can call the seesaw moving at, seesaw is at static equilibrium. Talking about seesaw, I forgot to give an example. Okay, so take the seesaw. Now, Aman and Ryan, both of you want to play on the seesaw. Aman is over here, Ryan is over here. What's going to happen? Obviously, where Ryan is sitting, that part will go down, right? Because the weights are not equal. But how is it possible for both of you to be able to sit on the seesaw and balance it? What can you do? Ryan needs to come front. What's happening when you move forward? Huh? How is it balancing? What is actually happening? Tell me in physics using some formulas or anything that I taught you right now. Force is not decreasing. Force means weight. The weight is not changing. Okay, distance is decreasing. So what happens when distance decreases? Not force. Moment of force decreases. Understand? So let me just give some values. Say Aman is 10 kgs and say Ryan is 20 kgs. Okay. So, and this distance over here, say the distance is 6 meters. Okay. Here also say it is 6 meters, obviously, because theta is balanced on both the sides. Now, if both of you are sitting at the edges, then what is the moment of force on the left side? And what's the moment of force on the right side? Now, left side, we'll call that clockwise or anti-clockwise moment of force?
No, anti-clockwise.
Anti-clockwise, okay? So what is the anti-clockwise moment of force over here? Force here is 10 Newton and the distance is 6 meters. So 10 into 6, that would be 60 Newton meter. This is the total moment of force that is exerted by Aman. Now, what would be the total clockwise moment of force? Yeah, that would be 20 into 6, which would be 120 Newton meters. So you can clearly see that the clockwise moment of force is more than the anti-clockwise moment of force. The resultant force would be how much? The resultant moment of force means when you add both. Now, how do you add both? Anti-clockwise is taken as positive. Clockwise is taken as negative. Remember that? So if you add these two, 60 minus 120, how much you'll get? You'll get minus 60 Newton meter. So minus means clockwise. So you will get a resultant clockwise moment of force of 60 Newton meter. Is that clear?
Now, to balance the weight, how much meter does Rand needs to come?
Let's find that out. Okay. So what we're going to find out now, how close Ryan should sit to the pivot so that the anti-clockwise moment of force is equal to the clockwise moment of force. Okay. So what we have now, okay, let's write them as values. We'll write them as F and D. F1 is how much? F1 is the force exerted by Aman, that is 10 Newton. D1 is the distance at which Aman is sitting. What is the distance? 6 meters. On the right side, what is F2? 20 Newton. And we want to find out what is D2. That means how far Ryan should sit from the pivot. That's what we want to find out right now, D2. So we'll write the statement. If the seesaw, your aim is to balance the seesaw. Your aim is to have equal anti-clockwise and clockwise moment of force. Right? Not force. Moment of force. Your moment of force should be equal. So we'll write the statement that is anti-clockwise moment of force is equal to clockwise moment of force. In other words, F1 D1 is equal to F2 D2. Right? The formula for moment of force is F into D. So anti-clockwise moment of force F1 into D1 should be equal to clockwise moment of force, which is F2 D2. Now we have the values for F1 and D1. That is 10 into 6 should be equal to F2 is 20 into D2 we have to find. So make D2 the subject by taking 20 on the left side. So we can find D2 this way. So cut 0 and 0, 2 and 6. So what is D2? 3 meters. So that means instead of Ryan sitting 6 meters away, he has to sit 3 meters away, somewhere over here.
Ryan sits 2 meters away, then when say my weight for
yeah, then your moment of force will be more and you will go down. Okay, so this point is where Ryan has to sit to balance it. If he sits anywhere front of this, then he will go up, Aman will go down. If he goes more to the right, then Ryan will go down, Aman will go on top. Okay, so like that, how much ever force you're applying or how much ever weight you have, you can always balance the seesaw by sitting at different position. Have you ever tried that on a seesaw when you're small? Never? How you tried? You'll go back, no?
Yes.
Like if you want to go down, you'll go back. See, automatically you do that. Why you're going back? Because the farther you go, you're increasing the distance. So your moment of force increases and you go down. You've done that?
Yeah.
Yes, I remember doing that when we were small. Like we go back and try to use our force, but we're not using our force. What we're actually increasing is the distance. When you increase the distance, the moment of force automatically increases. Okay, so you'll have this is one type of numerical that you'll have from this chapter. F1 D1 is equal to F2 D2. And out of these 4 values, one value will be missing, and you'll find that missing value. Okay. So we were talking about static equilibrium. Static equilibrium is like this. When the anti-clockwise moment of force is equal to clockwise moment of force and the objects are balanced, not moving anywhere. That is called static equilibrium. Another example, if a book is lying on a table, the book is exerting a force downwards and the table is exerting a force upwards. That force exerted by the table upwards is called a normal reaction force. Normal reaction force. That normal, when both the forces are equal, the book stays in that position. What if the book exerted more force than the force the table exerts? The table would break and the book would go down. Okay. Yeah. So this is another example of static equilibrium. Another example is the beam balance. If the beam balance is steady, that means both the weights are equal on both the sides. Beam balance will stay steady, right? That is another example of static equilibrium. Okay. So for dynamic equilibrium, our object has to move. But how should it move? At a constant speed. So let's read this. When a body remains in the same state of motion, that is translational or rotational. Translational means in a straight line, rotational means rotating. So either it is moving in a straight line or it's moving in a rotational direction. But if the speed is constant, then it is dynamic equilibrium. So under the influence of several forces, so many forces are acting on it, and because of that, it is continuously rotating or moving in a straight line. So examples are a raindrop. When a raindrop is falling to the earth, is it translational or rotational? Could be both. Like if you see the whole raindrop, it is moving in a straight line, but the drop might be rotating also. Okay, so there are both the forces felt on that raindrop, but it is a constant force, and so it is a dynamic equilibrium. Here they're only talking about the speed at which it is coming down. So it's moving at a constant speed. Next, an aeroplane moves at a constant height when upward lift on it balances its weight downwards. See, as the aeroplane is moving, there are forces acting downwards and upwards. What is the forces acting downwards? Yeah, but what is causing the gravity to pull it downwards? The weight of the aeroplane, the weight of the passengers, the weight of the whole aeroplane is what pulls the aeroplane, or the force that pushes it downwards. And what is the force that pushes it upwards? Yeah, the air and the wings of the aeroplane that cuts through the wind and tries to pull it upwards. There are the two forces acting. The weight is pushing downwards, and the wings of the aeroplane with all the propellers and motors and everything is trying to push it upwards. So when both these forces are equal, the aeroplane will stay at the same constant height. Right. If he increases the speed of those fans and propellers, then what will happen to the aeroplane? He can make it go higher up, adjusting the wings. And if he reduces the speed of it, it will go down. So if both the forces are equal, it will stay at a constant height. Then next is a stone tied to the end of a string, and then you keep rotating it round and round. Okay. So now the stone is moving at a constant speed. Okay. So that's another example. About the stone, we'll be studying later on about the two forces, centripetal and centrifugal forces. Okay, that comes a little later on. Now, what are the conditions for a body to be at equilibrium? Two conditions. First is the resultant of all the forces acting on the body should be zero. Both of them are almost same. Let's read the second one also. The algebraic sum of moments of all the forces acting on the body about the point of rotation should be zero. Okay, so let's take the same example of seesaw with 10 people sitting on the left, or 5 people on the left side and 5 people on the right side. Okay, so different people are sitting at different positions, and each of them are applying a certain moment of force. I'm not talking about force. Force is just their weight. Talking about moment of force. That is their weight into that distance. Okay. So say a person over here is applying a moment of force of 50 Newton meter. Should we write this as plus 50 or minus 50?
Yes.
Why? This is anti-clockwise. Anti-clockwise is plus, right? Okay, so here we have a plus 50. Then here you have another one. Maybe that person is very heavy, and even though the distance is less, he might apply more moment of force. So it could be 60, right? Then maybe another person over here is applying a moment of force of 20 Newton meter. Okay, all right, let's just take three for an example over here. Okay, now on this side also you have, say, two people. Let's remove the 5 and the 5. Okay, on the left side, how many people I have? 3. On the right side, I have 2. So say this person is applying a moment of force of 40 Newton meter. And here the person has a moment of force of 90 Newton meter. Okay. Now these two are negative because it's making it go clockwise. Now add all the moment of forces that are anti-clockwise and add all the moment of forces that are anti-clockwise. Clockwise. How much will that come up to? No, separately add them. Anti-clockwise 120. 120? 130. So 130 Newton meter. And clockwise moment is minus 130 Newton meter. Okay. So look at the second one. It says the algebraic sum of moments of all the forces. That means if you add all of this plus all of this, how much do you get? Zero, right? 130 plus this minus 130, it adds up to zero. So this is what the second condition is. The total sum of all moment of forces around that pivot, around that point, should be zero. Okay. So then we say that this object is at equilibrium. By the way, what type of equilibrium is this? Static or dynamic? This is static because it's not moving at all. A seesaw, three people here and two people here, and their moment of forces are equal on both sides. The seesaw is not moving at all. So that is static equilibrium. Okay. Uh, the first condition also is similar to this. The resultant of all the forces acting on the body should be zero. So the total forces acting on this body should be zero.
You say people sitting in a car with a constant space. Will the people will feel dynamic equilibrium?
Not people, the car.
The car is moving.
Yeah, but it's moving at a constant speed, no?
So what about the people sitting inside?
Ah, okay. The whole car with the people are at dynamic equilibrium because they're moving at a constant speed. Okay. Okay. So from all this, what you've understood, static equilibrium means the body is not moving at all. There are many forces acting on it, but it's not moving because the total sum of all moment is coming to zero. And dynamic equilibrium means what? It's moving, but it's moving at a constant speed. Okay. Write down whatever you have to write down. So I think from where? Okay, first for this you write down the heading. Um, Here, anti-clockwise moment of force is not equal to clockwise moment of force. I'm writing a statement here. As the seesaw is balanced, therefore anti-clockwise moment is equal to clockwise moment of force. Okay, we have just 1.5 minutes. Just let's look at this example over here. Right, first. See here. Okay, pause. See in this diagram, you can look at the diagram. You can clearly see here the distance is 2 meter, and on the right side the distance is 4 meter. So on the left side there's a force of 5 Newton. On the right side there's a force of 3 Newton. So the first question is, what is the moment of force F1 about O? F1 is on the left side. So what is the moment of force of F1? What's the answer? F into D. That is 5 into 2. 10 Newton meter anti-clockwise. Now for right side, what is the total moment of force? 12. 12 Newton meter. So what's the total moment of force? So clockwise and anti-clockwise you add or minus. So 10 minus 12 or 12 minus 10, you're getting 2 Newton meter clockwise. So do all the questions till the fourth one. Okay. Numericals 1 to 4 is your homework. Yeah, I'll see you in the next class.